Okay, so reversible reactions is what we're talking about today. Now, in chemistry, you will find that chemicals such as this green atom here and the red-blue molecule are going to react spontaneously to give you a chemical reaction. Okay, the products in this specific example are the green-blue molecule and the red atom. Okay, now sometimes you will get reversible reactions, and what that means is that once all the green atoms and the blue-red molecules have reacted to give your products actually want to react to form the original reactants. In that case, we have reversible reactions. So you can see in this second bit here, we've got the reactants reacting together to form the products, and then the products themselves are reacting together to form the original reactants. We don't know why this occurs, but sometimes it does. Now, in this instance, you will have both of the directions going. These directions are known as the forward direction and the backwards direction. So forward meaning the formation of the products, and backwards meaning the formation of the reactants. And there is a point at which both of the directions are occurring simultaneously. Now, when the rate of each of these directions are at that same value, so they're producing at the same speed, you won't actually know that the reactions are occurring, because the breakdown of this molecule will coincide with the formation of one of those molecules. So the concentration of all of your chemicals will remain constant, despite the fact they're continuously reacting. Other traits to note about the equilibrium is that it always happens at the same point. So equilibrium is when that rate of forward and reverse reaction is equal, when the concentrations of each of the chemicals aren't changing. And each reaction has a point that it will reach equilibrium. We know this as the position of equilibrium, which is assigned the letter K, capital K. Okay, so if you start with all of substance A, it will break up to form B and C. Eventually B and C will start combining to become A. These reactions happen until they reach equilibrium. They reach equilibrium at the same point if you start with all B and C or half A and half BC. It doesn't matter. Okay, so your K value will be a consistent value for each of the reactions. Something to think about for your EI in a few weeks. Okay, so going here, I want to relate this to something that you may know. So hopefully a lot of you are driving at this stage. Now, you may have noticed that the highway can have quite a bit of heavy traffic at certain points in the day between the Gold Coast and Brisbane. Now here I've got at midnight, so you can see the times at the top here, okay, midnight, and then you can also see the population of both locations. Now obviously there aren't 100 people or 100 cars on the Gold Coast and 100 in Brisbane, but I wanted to keep the values simple. Okay, so we have midnight here. There are 2 cars going north and there are 2 cars going south. Therefore, it is at equilibrium. Okay, so this is at equilibrium, which means that the rate of cars going north and cars going south is at the same, so the population remains the same. You can see this because at 2 AM, the population hasn't changed. It's still 100 in each of those locations. Also, the traffic at 2 AM is the same in both directions, so it's going to stay consistent for both the populations of Gold Coast and Brisbane. 4 AM is also very similar. You have the same number of cars. Now once we get to 6 AM, we are getting the morning traffic. Okay, so you can see here, you've got extra cars that are driving up to Brisbane. Your population of the Gold Coast has dropped from 100 down to 90, and in Brisbane, 100 up to 110. So the increased rate in the northbound traffic has caused a change in the population or a change in the concentration. The cars going southbound down to the Gold Coast have remained consistent the whole time, so they aren't gaining any. As you go to 7 a.m, the same thing occurs. You've got those extra cars there. The population drops down even further, 90 to 80 and 110 up to 120. This is going to be consistent while you do have that morning traffic, and because the rate of northbound is there's a lot more cars on it than on the southbound, it means that the highway at this time of the day is not at equilibrium, because in order to be equilibrium, it must have that same rate. So we're down to 70 and up to 130 by 8 a.m. Okay, going to midday. Can you see here that we've got 70, which is consistent, and 130 consistently. So over the 4 hours since 8 a.m, we have been able to reach equilibrium again, where the cars going north and south are at the same speed, at the same rate. Okay, going to 2 p.m, they remain the same. We've still got the same populations and the same rate. 4 p.m. is when the early people start to make their way back home. So you've got 70 going up to 80 and 130 going down to 120. As the rate of the southbound increases, but the rate of the northbound has not increased. Now this will stay with us until the end of the night traffic. So 5 p.m. you've got it even more, and the population is changing. In respect to that, 6 p.m. you've got the same, so it's back down to 100 and 100. Now between 6 and 8 p.m. the traffic has been able to reach equilibrium again, and the concentrations or the populations of both the Gold Coast and Brisbane are at that same value at 100. The value of the populations or of the concentration isn't actually important when you are looking at equilibrium. The rate of the two different directions is what is important for equilibrium. Okay, and then going down to 10 p.m. you can see that there's no more traffic issues. Now just before I end this video, I wanted to talk to you about another term called Le Chatelier's principle. This refers to when you have an equilibrium and you are basically going to make an external disturbance or try to screw up an equilibrium. What will happen is initially it will be a bit chaotic, but then the reactions themselves will cope by trying to minimize the disturbance that was made on it. They will eventually reach equilibrium again. However, the position of equilibrium, okay, the concentrations that they reach will not be the same. So your original position of equilibrium, which I told you had the letter K, is your theoretical position of equilibrium when everything is going normal. When you introduce in disturbances causing Le Chatelier's principle, your position of equilibrium is most likely going to change. Now this here says that in chemistry, obviously, your disturbances can be anything like concentration, temperature, or pressure. So if I increase the concentration of something, the system, the reactions themselves, will try to decrease that concentration by consuming that chemical. If I increase the temperature, it will try to create a reaction that decreases the temperature, effectively neutralizing the disturbance that I made. And if I decrease the pressure, it will attempt to increase the pressure back to the normal state. By doing this, your equilibrium will shift. Okay, so the shift in the position of equilibrium can be determined by calculating Q. Now Q is exactly the same as K. It just refers to the position of the equilibrium after a disturbance. So it's an experimental value. It's not necessarily something that is unique to that reaction. If you are able to calculate Q and you do have values, if you are able to calculate K and you do disturbances on your equilibrium and are able to calculate Q values, then you can use this last bullet point here by comparing the values. If your Q is smaller than your K, then you know that your equilibrium has shifted to the right in your chemical equation or in your chemical reaction. If Q is equal to K, then Le Chatelier's did not cause a shift in the position of the equilibrium. It was able to get back to its original position. And if Q is larger than K, then the equilibrium was shifted to the left. We'll be doing examples of these in class. Bye.